Don't you wish you could turn those lipases on a little more often? Okay, so now we're going to take a big look at what you do with your fatty acids. We're going to really spend a long time focusing back here on the process of turning fatty acids into acetyl-CoA. If you notice, we already know what happens to it from there, right? Acetyl-CoA goes off to the citric acid cycle. And this is where this is important again. Remind me, and I'll keep bringing this up, but acetyl-CoA, when it goes through one full round of the citric acid cycle, what do we get? 1 ATP, 1 FADH2, 3 NADH. This is going to be important. When you start calculating, the result of beta oxidation of, some fat or something like that, you can memorize a formula. And that formula usually doesn't make a whole lot of sense to anybody, which means the likelihood of you remembering it longer than, say, Monday at 5 is not very good. But if you know the process, you can pretty quickly, actually, without even a formula, total out, what the ATP count is really going to be. So we'll see that in a minute. All right, so you got this fatty acid here. This R group, how long is this R group probably?
16.
Could be 16, could be 18, could be 20. If we're in a plant, it could be shorter even. Coconut oil, 12 and 14s, stuff like that. So it's variable length. I don't want you to think, though, that this is really short, even though it just says R. That's some sort of long chain fatty acid. Cool, first thing that has to happen is we need to activate that fatty acid. So in activating it, we're going to make it an acyl-CoA. So we're going to have that high energy thioester linkage that we've seen a number of times in a variety of places. So, and it's acyl-CoA synthetase that actually does this. What does it cost to do this? Sort of 1 ATP. It's really going to cost 2 ATP. It's kind of weird. So your ATP, when it gets hydrolyzed, doesn't get hydrolyzed to ADP. It becomes AMP. But this pyrophosphate here as well further gets hydrolyzed into 2 inorganic phosphates. And so you're breaking between ATP going to AMP and pyrophosphate, you broke one high energy phosphate bond. But then when you hydrolyze pyrophosphate into 2 inorganic phosphates, you're breaking another high energy phosphate bond. And it's really the equivalent of 2 ATPs. And so for accounting purposes, from here on out, we're just going to say it's 2 ATPs, even though it's not necessarily actually, going from 2 ATPs to 2 ATPs, but it's the equivalent of using up 2 ATPs. So the activation process, so for beta oxidation, as we'll see, is going to cost 2 ATPs. What's really nice and convenient, is what was the energy investment for glucose in glycolysis? What was the upfront cost? 2 ATPs. It makes it really easy to remember that. Nice and convenient. For beta oxidation, the upfront cost is also 2 ATPs. Correct, but again, the key is ATP is getting hydrolyzed not into ADP. What's it becoming? AMP. So it's not going to ADP, which would be breaking one phosphate bond. It's going to AMP and then pyrophosphate. So, but when you see pyrophosphate formed here, the assumption is that it also gets hydrolyzed to 2 separate inorganic phosphates. And so you're going to break a second phosphate bond. So breaking one when ATP turns into AMP, you're going to break another when you hydrolyze the pyrophosphate. So breaking 2 phosphate bonds, we're going to say it's the equivalent of having used up 2 ATPs. So you're not really, using up 2 ATPs. Only 1 ATP is involved, but it's the equivalent energy-wise of having used up 2 because you're going to break 2 high-energy phosphate bonds. Cool. Sweet. So now we got our acyl-CoA, and life is sort of good, but we got a problem. This happens and is formed in the inner membrane space. I need it to get into the matrix. And acyl-CoAs don't do that. So acyl-CoAs don't cross. So we have another shuttle to get us across the membrane. Notice we've talked about quite a few shuttles between last review and this one. Here's another one, the carnitine shuttle. So we're going to take our acyl-CoA and we are going to hand off our fatty acid here to carnitine because acyl carnitines can cross the inner membrane. So then once it crosses the inner membrane, so I can turn it back into an acyl-CoA. So neither one of these steps requires ATP at all or anything of the sort. So, and the enzymes that do it are called carnitine acyltransferases. The first one is, go figure, carnitine acyltransferase 1. The second one is, that's supposed to say carnitine acyltransferase 2. My bad. So fix that. and I'll fix it eventually before I post this online. Cool, these are just two different carnitine acyl transferases. One transfers the acyl-CoA to carnitine, so it transfers the acyl group anyways. So the other one just transfers it back once it's on the other side of the membrane. So beta oxidation, you're supposed to think that's fatty acid catabolism. So somebody brought up, beta oxidation earlier, and while we're doing other types of oxidation, like, we're doing glycolysis, we're oxidizing glucose, but that's not beta oxidation. Beta oxidation is the specific term we reserve for oxidizing, catabolism of fatty acids. So if you look here, and taking a fatty acid, so beta oxidation ultimately turns your carbon fuel into acetyl-CoA molecules. So, quick review. First thing we got to do to our fatty acid is activate it. We'll turn it into we'll turn it into an acyl-CoA. So we'll use the carnitine transferases to get it inside the matrix, but then we'll again get it back to being an acyl-CoA. So now that it's an acyl-CoA, now the real fun begins. There are 4 steps to this process. So if your organic chemistry has been a little while, this could seem a little bit rough, but this is important, all 4 steps. So first step's oxidation. So, and if I'm doing an oxidation, what has to accompany it? Reduction. So no big surprise that we're producing FADH2. Welcome. So if you look, the third step is also going to be oxidation, and no big surprise accompanying that is the production of NADH, a reduction. So, but first step oxidation, then hydration, again oxidation, and last but not least, thiolysis. That'll be good times. So if we look along the way, I highlighted the last 2 carbons. In beta oxidation, we chop up the molecule 2 carbons at a time, so to speak. So if I have a 16 carbon chain, let's say, so how many 2 carbon pieces can I chop it up into? 8. So, and each of those 2 carbon pieces is going to end up being an acetyl-CoA. So in this case, we're going to focus on those last 2 carbons. So at the acyl end of our fatty acid, because those are the 2 that are going to get chopped. We're going to chop it right there, so, and make an acetyl-CoA molecule out of that. So first thing we do is oxidation. And notice oxidation, this is specifically just a dehydrogenation here. We're pulling hydrogens off 2 adjacent carbons, forming an alkene. And if you recall some of your definitions for oxidation, so we often look at it specifically from oxygen's perspective, but we could throw some other atoms in there. But if we look at it from oxygen's perspective, oxidation could be gaining bonds to oxygen. And usually look at 2 happening at a time. So if I gain 2 bonds to oxygen, great, that would be oxidation. But you don't just have to look at it as gaining bonds to oxygen. Who could you be losing bonds from? Hydrogen. And this is also therefore oxidation. This carbon is losing a hydrogen, and this carbon is losing a hydrogen, forming an alkene. That is indeed an oxidation step. Cool. Acyl-CoA dehydrogenase is the enzyme. I think it's worth knowing the names of each of these enzymes and knowing all 4 steps. Also knowing where we might get some reduced cofactors. Second step is hydration. What does hydration mean? Adding water. And when you add water, so you guys did 3 different water additions back in OChem back in the day. He did acid catalyzed hydration, oxymercuration, demercuration, and then hydroboration oxidation. Bet you thought you'd never have to hear those ever again. But they were hydration reactions. You started out with an alkene. So the alkene, you underwent an addition reaction, and you had an H and an OH. And you might have done it Markovnikov or anti-Markovnikov. So I don't really care about any of that stuff here. But hydration is when you add H and an OH across an alkene in this case. There are other reactions we might also refer to with hydrations, but that's what this is referring to here. And so in this case, the carbon on the left here is going to pick up the OH. The carbon on the right is going to pick up the H. It's just hydration. The biggest thing to keep in mind is this is not oxidation. A lot of students see, oh, we got an oxygen. It must be oxidation. Why is this not oxidation? Yeah, whereas this carbon gained a bond to an oxygen, this one gained a bond to a hydrogen, and so it's a wash. This is not oxidation, and it is not reduction. So keep that in mind. That's why there's no cofactors involved here. It is not redox. Cool. It is enoyl-CoA hydratase that does this. So now we've got a beta alcohol here. So at the beta position, if you forgot how that whole Greek letter alphabet works, your carbonyl carbon is ground zero. It doesn't get a letter in the Greek alphabet. The first carbon next to it is alpha, then beta, gamma, delta, epsilon, so on and so forth. So if you didn't join a fraternity or a sorority, you can kick yourself now. All right. Next step is your alcohol is just going to get oxidized. When you oxidize a secondary alcohol, you're going to lose one bond to a hydrogen and gain a second bond to that oxygen, and voila, we end up with a ketone. And so your beta alcohol oxidized up to a beta ketone. Losing a hydrogen and gaining an oxygen, that's oxidation. And again, being oxidation, we are going to need to reduce a cofactor here, NAD plus going to NADH. So, by the way, one, I didn't put plus there. If you look, I've done this a lot throughout. So like when I go from ATP to ADP, it's really ATP goes to ATP plus what? Phosphate. Inorganic phosphate. I never write it. I want to keep it as simple as possible, but it's there. Same thing here. So when you go from NAD to NADH, a proton is also involved there. I never write it. And I will never write it on any slide you see tonight, but it's still totally there. And it's important because that's actually part of the proton gradient in both electron transport as well as photosynthesis is the fact that protons are involved in that little process as well. But I'm just never going to write it. I'm going to try and keep this as simple as possible and not try and cloud it up too much. Okay, so if you look here, the goal, we needed to get the beta position to be a carbonyl. That's the whole goal of everything we've done up till now. Because what we're going to do is we're going to break this bond right here. This molecule right here is going to be what? That's going to be acetyl-CoA. I'm going to bring another coenzyme A in to attach to this one. And so it's going to make the existing rest of the chain also an acyl-CoA of some sort. And so here we get our acetyl-CoA from those two carbons in blue. So, and then right here we get our acyl-CoA. And I'm going to help you guys out just a little bit. Cool. So one cut here, and we got one acetyl-CoA and the rest of the chain. And then we'll just repeat all 4 steps. So again, I will go through oxidation, hydration, another oxidation, and thiolysis again to produce another acetyl-CoA. And I'll do this again and again and again until all I have is a bunch of acetyl-CoAs. Cool. Every time we do this, what cofactors do we get? Every cycle of 4 steps. 1 NADH and 1 FADH2. So that is something worth remembering. So every time you cut your fatty acid, every time you chop 2 carbons off to make acetyl-CoA, 1 FADH2 and 1 NADH are produced. So we're going to do an accounting here. So I would highly recommend, there are formulas you can use for calculating how many ATP you get and stuff like that. So, and students routinely jack that. If you can just simply keep in mind what's happening in the process, I guarantee it's not that bad figuring out how much ATP is going to be produced here. So now let's look at the big picture. We're going to follow a giant long-chain fatty acid from start to finish through every cycle it could possibly go through. So if we look, this is stearate. This is stearate, or stearic acid, same diff. It's the conjugate base form. It is 18 carbons long. How many acetyl-CoAs am I inevitably going to chop this up into in beta oxidation? I'm going to get 9 acetyl-CoAs. Now, one really important thing you need to keep in mind, if I'm going to break this long chain up into 9 pieces, how many cuts do I need to make?
18.
Only 8. Notice just 1, 2, 3, 4, 5, 6, 7, 8 cuts to get 9 pieces. So one of the biggest mistakes students make is they see 18 carbons and they think, oh, I'm going to get 9 acetyl-CoAs and I must do 9 rounds of beta oxidation, but it's not. It's only 8. So with 8 rounds of beta oxidation, well, every round of beta oxidation produces what? 1 NADH and 1 FADH2. And so with my 18 carbon chain, if I'm going to go through 8 rounds of beta oxidation so that I'm going to get 8 NADHs and 8 FADH2s. I'm also going to get my 9 acetyl-CoAs. What am I going to do with those acetyl-CoAs? Send them off to the citric acid cycle. And this is why I brought this up before. Every acetyl-CoA that goes through the citric acid cycle gives me how many ATPs? 1. How many FADH2s? 1. How many NADHs? 3. Sweet. And I'm going to shuttle 9 of them through the citric acid cycle. So that's why I'm not going to just get 1 ATP, I'm going to get 9 ATPs. Notice it's initially produced as GTP, but that's the same thing, really. It's equivalent to 9 ATPs that get converted there anyways. But I also get 9 FADH2s, but 3 times 9, 27 NADHs. So just keeping an accounting here. Cool. So in this case, if we look from start to finish, let's not forget that what was our upfront energy investment to activate our fatty acid? 2 ATPs. So that's what we're going to cost 2 ATPs up front. So the beta oxidation produced, in this case, again, for a 18 carbon chain, we got to do 8 cuts, 8 rounds of beta oxidation. So that's 8 NADHs and 8 FADH2s. But then citric acid cycle pays off huge as well. So citric acid cycle, we're going to get 27 more NADHs, so 9 FADH2s and 9 more ATPs. So at the end of the citric acid cycle, we have now produced a grand total of 7 ATPs. We've used up 2 to activate our fatty acid. We've produced 9 in the citric acid cycle. But we have produced a whopping 35 NADHs and a whopping 17 FADH2s. And what are we going to do with those? We're going to pump them into the electron transport chain. And every NADH turns into how many ATP, roughly? 2.5 is the magic number there. So we'll take 35 times 2.5. That's 87.5 ATPs. And all 17 of our FADHs get cashed in for how many ATP? 1.5. And 17 times 1.5 is 25.5 ATPs. So from the NADH, we got 87.5 ATPs. From the FADH2, 25.5 ATPs. And we've already produced 7 ATPs. And you add them all together, and voila, you get 120 ATPs. So, and again, keep in mind, if you see this again in some other class, you might use slightly different ratios for how much ATP you get from NADH and FADH2. But for this class, those are the numbers you definitely want to use. Cool. Rather than coming up with a formula, I would recommend you just work your way through the process. So work it through a couple times on your own, but you can definitely do this in less than a couple of minutes. Cool. One more thing to talk about. Want to go right back up here. So far, we've really only talked about beta oxidation for saturated fatty acids. But we can also do this for unsaturated. So, and this can get complex in a hurry, but let's just assume for a minute a mono unsaturated fatty acid. What does that mean? One double bond. And if it's a natural fatty acid, in all likelihood, that double bond is going to be what? Cis. Well, it turns out to go through beta oxidation, it has to be converted to trans. So to be a good substrate, it has to be converted to trans. So in this case, the enzyme that does that, so it's on the bottom of your handout there, enyl-CoA isomerase. Just isomerizes the cis double bond to a trans one. So, but if you've got that trans double bond now, didn't take any ATP to isomerize it, by the way, but if you've got a trans double bond now, that's what's involved here, a trans double bond. If you just happen to already have one, then it doesn't take 4 steps to do beta oxidation. How many does it take? Just 3. I mean, you got that isomerization that has to happen at some point, but instead, we're just going to start from this point for a round of beta oxidation. We're going to do hydration. We're then going to do 1 step of oxidation, and then thiolysis. And so the payoff is not going to be as good anymore. So what do we get 1 less of in this case? FADH2. So if you've got a mono unsaturated fatty acid, you get 1 less FADH2. Cool. Technically, for polyunsaturated, so the convention is to say, you know, you lose 1 FADH2 for every double bond. But the picture actually gets a lot more complex than that. It was in one of his slides. I'm not going to talk about it. I didn't see any question relevant to talking about polyunsaturated fatty acids and beta oxidation on any of his practice exam material. So, but there was a slide going over it. It's a really complex process. It's really good times. So, but in polyunsaturated, you also might start using up some of your NADPH, which kind of muddies the picture of what the energy payoff is. So, but simple perspective though, so for every double bond, 1 less FADH2. So let's go back here a second. If instead of stearate here, stearic acid, let's pretend I'd had one double bond in that 18 carbon chain. Instead, how would the picture be different for total ATP production? Minus 1.5. So, because instead of 17 FADH2s, how many would you get? You just get 16, and you'd have to subtract off 1.5. And so your total ATP instead would be like 118.5. Cool?
Does it matter where the double bond is on the...
So does it matter where the double bond is? It actually does. If, as you start chewing this up 2 by 2, if the double bond doesn't end up in the proper location, so you actually have to go through a roundabout process to get it in the proper location. You actually end up reducing it and then reoxidizing it, and it gets a little crazy after that point. And this is the problem with polyunsaturated as well, is you got many double bonds, odds are somebody's not going to be in the right place, and it gets real confusing. So I'm not going to go too much into it, but suffice to say, at this point, I would say one double bond, one less FADH2.